Exercise 3.19. Show that if A is closed in X and B is closed in Y, then A times B is closed in X times Y, where we're taking the product topology on X times Y. All right, well, here's a picture of A times B. If A is a closed subset of X and B is a closed subset of Y, then in this sort of depiction, the product A times B would look like a closed rectangle. In order to show that it's closed, we have to show that its complement is open, right? And so my strategy for doing that is going to be to show that the complement can be written as a union of these two sets, each of which is open, and therefore the complement's open. Okay. This set is sort of everything above the rectangle and below, and this set is everything to the left and the right of the rectangle. All right, so that's a good diagram, but let's see if we can write out a proof with that idea in mind. Okay. So first, we would like to note that the complement of A times B, so X times Y minus A times B, is equal to, well, X times the complement of B in Y union, well, the complement of A in X times Y. Okay. So I will come back and prove that statement in a bit, but let's just take it on faith for a moment. Okay. Well, since A is closed, the complement of A is open, right? And since B is closed in Y, the complement of B in Y is also open. Since each of those are open, each set in the union is open, right? Because not only are those two open, but X is open in itself, and Y is open in itself. So everything you see here on the right side is open. And if we take a product of an open set in X with an open set in Y, that's a basis element in the product topology. So it's certainly an open set in the product topology. Okay. And so, well, hence, the right side, which is just a union of these two open sets, is an open set in the product topology. Right. Well, if the right side is open, the left side is too. But the left side is just the complement of A times B. And therefore, if the complement of A times B is open, A times B must be closed. Right. So thus, A times B is closed, which is what we wanted to prove. All right. So if I can just convince you that this big ugly equality up here is true, then we'll be done. So let's write that down. Proof of, let's just copy it. Okay. Well, what I'm going to do is show that an element being in the left side is equivalent to it being in the right side. Okay. So say that xy being an element of the left-hand side is equivalent to, well, what? Let's see. That means that xy is in X times Y, and it's not in A times B. Right. Good. And that, in turn, is equivalent to, well, what does it mean that xy is in X times Y? It means that X is in X, and Y is in Y. Right. So we have that, and then what does it mean that xy is not in A times B? Well, it means that either X is not in A, or Y is not in B, or both, right? Okay. Next, we can move some things around there. Okay, so if x and y not y, and one of these is not the case, could be rewritten as, well, x in x and well, x is in which one? Let's see. I'm sorry, I should say and y is in y, right? And not in b. So y minus b. Or the other possibility is that we still have x in x and y in y. And we have x not in a, so I'm going to amend this to say that x is in x and it's not in a. Okay. So those two are certainly equivalent. And then we're getting pretty close, because for x to be in x and y to be in y minus b, that's equivalent to saying that the point xy is in the set x times the set y minus b. So we have that, or the point xy is in the set x minus a times the set y. Right? And now you see where the union comes from. Copy the right side of my equation up here. If the point xy is in one or the other, then we can say that it's in the union. Okay. So we're done. We have shown that a point xy in the set x times y is in the complement of a times b, if and only if it's in this union on the right side here. That finishes our proof.